we'll jump into the usage of MK1 in FiftyOne. That being said, I'm going to go ahead and turn it over to Akshat. Akshat, the floor is all yours.
Thank you. Give me 1 second. Can you all see my screen?
Yeah, yeah.
All right, cool. We'll get started. Well, thank you, Harpreet. So I'm Akshat, the co-founder and CTO of Perceptron, and I'm here along with Eric, who you'll probably see in the call as well, who's driving product here at Perceptron. So we're both here to talk about this. So as Harpreet alluded to, today we're here to talk about MK1 or Mark 1. This is our frontier model for the physical world. The goal of this talk is to first talk a little bit about the thesis behind the reasons we build models and release them, what are the kind of things we do, talk about some of the challenges we faced on the technical front, how we design and solve for them, and how you realize that, and then really talk about what it means to be at the frontier here. And that'll lead into the kind of capabilities that our model enables that others struggle with. So let's get started. So taking a step back at what we're building to do at Perceptron and what are we really after in our mission here? So our goal is to build physical AI. And what this really comes down to is we want to build models that can perceive, understand, and interact in the physical world, all at real time and at a deployable cost. The goal here is to bridge the physical and digital world together, and we believe that the missing component here is in the AI layer. A lot of the models today, which we'll talk about in a second, struggle to operate in the real world, and we'll break down why that actually happens. So the core thing to take away here on physical AI is to break it apart from cognitive AI. And these essentially are the two dual axes for how we think about AI development in the modern day here. So when I talk about cognitive AI, majority of foundation models today fall into this domain. It's essentially reasoning over symbols. You care about text, which is human written content. You care about structured data, code, very discrete question answer periods, and you really just want to get some answer that knowledge that a human has. It's some form of question answering, and you really want to shine on intelligence. And this ends up being the way that most AI labs today define what their goal and their definition of AGI is. But there's essentially this dual axis in the physical world, where the physical world isn't the same as the digital one. It's not built to operate on the internet. It's not as clean. It's not as structured. It ends up being very continuous. Information is sometimes abundant and sometimes there's very little of it. It's super multimodal by nature. Language is present, but the majority of the world tends up being in vision and audio. Uh, and the world's essentially operating at whatever the real-time throughput of the world is. You can't pause the world while it's going on, so things need to be fast and efficient. And that's the functional difference in cognitive and physical AI. And so what you'll see is today's foundation model labs are all going after this definition cognition. So they want to go and solve math problems, they want to solve biology problems, they want to solve reasoning problems. And the way to do so is to build systems that solve truly difficult problems, but spend more on doing so. You want to get to the point of replacing a human in knowledge and reasoning, regardless of how long and how much compute it takes. This doesn't end up working for the physical world, and it breaks apart in pretty simple cases. So take this example here. And this is essentially the simplest example that's there right now on where cognitive AI starts to fail and where models optimized for the digital world don't generalize super well. So there's a picture here of a hand which has 6 fingers. And if you're training your models to operate on these kind of general internet and digital problems, you have a lot of biases of what should happen inside of images. And you tend to think of things as very structured, very general. You'll understand there's a hand, and you'll assume that there's 5 fingers on this hand from that. And if you're reasoning over the internet, it's actually like a fairly it's not a huge problematic thing to do on the internet. Now, what happens is that there are improvements where foundation models make the perception, but they require going down routes to something like thinking. Uh, so now you have to spend more, wait longer, and get a response to get something as simple as perception working of just counting the number of fingers that are there. Like you can try this right now with GPT 5.5 Instant versus thinking. Whereas the goal behind our models, whether it's the Mark 1 series, the Isaac series, and we'll talk about the distinction between the two of them, is that this kind of perception should come for free within the model itself, and this is natural for the model to respond to immediately without having to spend significant amounts more worrying about reasoning or anything like this. So that's generally where physical AI differs from cognitive AI. So what we're doing at Perceptron is we're building a series of models that's meant to accomplish the full spectrum. Now, what we acknowledge is that unlike the digital world and unlike the cognitive world, not everything can be deployed through cloud. Uh, there are various deployment surfaces. You might want things to run on device, you might want things to run locally, you might want to run in regions without internet, um, and you might want to be able to run on cloud as well. And you might have different trade-offs. In certain cases, you care more about latency, in other cases, you care more about accuracy. So we've done one of these talks before with Harpreet on where we've been working on Perceptron and Isaac, which is our open source series of models. These have all been released. We continue to iterate on them. You can think of them as around 2 billion parameter models that are out there aimed at operating at the frontier of image reasoning in the open source community. So go check them out. We're not going to focus too much on them because the new thing here has been our frontier model. And this is our closed source model Mark 1. So this frontier closed source model ends up being a much larger model that we end up working with. Actually, we've had this model for quite a bit of time. We use this to create the Isaac models. They're essentially distilled versions of Mark 1. But we realize that the community probably wants access to something that is actually frontier and it may be in cloud, but it's at a deployable cost. And that's where Mark 1's meant to sit. So there's a few novelties that Mark 1's introducing, which we'll dive further into. But one of the big ones is video native, and it's really at the frontier of video and embodied reasoning. Let's use that apart. Okay, so now for the rest of the talk, we'll focus on Mark 1 and what we've been up to here. So Mark 1 essentially defines the efficient frontier. And so in physical AI, we've identified these two big domains that people are relying on models for. One is in video understanding. A lot of the physical world has naturally videos inside of it. And the second is embodied reasoning. So this can relate to anything from robotics to perception robotics to different kinds of spatial reasoning, things you expect from agents that are deployed in the actual world to have to be able to do. And they're not all robotic centric, like even a camera is an embodied deployment in the physical world. So it's really just an agent that's actually present in the world falls into embodied reasoning. And so if you look at the current spectrum of models today that support multimodality to address these two domains, you can essentially break down their performance across all open benchmarks here. This is all on our blog post. You can see the exact benchmarks that went into this report against the cost themselves as well. So to understand these axes a little bit more, the mean score here is on quality of both the video and embodied reasoning benchmarks, normalized to 0 to 100. So 100 would be a perfect score, 0 would be everything's failing. This is where everyone lies right now. And the important part here is the blended cost of these models per million tokens. And the realization is for multimodal heavy use cases, you tend to have a very large breakdown of input versus output. So you tend to be something like 90% of your tokens are input tokens because they tend to be image and video, and only about 10% of them are output tokens, and this is presented at log scale. So the existing frontier of models from Google, such as Gemini 3.1 Pro or GPT-5 from OpenAI, there's a Sonnet series from Anthropic, and the Qwen series from Alibaba. All perform multimodally, but they essentially struggle in one of two ways. There's a class of models that essentially fall beneath Mark 1 that just don't have the capabilities needed to be effective in multimodality. And this comes to both video reasoning, image reasoning. They just struggle to accomplish these cases, like the one we showed earlier of just counting the number of fingers. The other is that there's a set of models like Gemini 3.1 Pro that actually excel in this domain and even outperform. But the cost here ends up being 10x more. And so if you're someone that's trying to deploy on your large scale of images, or you're trying to deploy on 24/7 video, or any real-time or continuous deployment scenario, this cost of just being 10x more isn't just simply a cost lever. It can make your camera cost $10,000 to $20,000 a month to run versus costing as low as $100 a month to run. And the difference in price here isn't just this gradient scale. It's actually if something costs $10,000 a month to run, it might not even be worth considering. You need to be at this price point where things are actually deployable. And that's a big focus of us delivering models at Perceptron, is that whichever deployment surface we target, whether it's cloud, devices, open source, or closed source, the models are designed to actually be in a realm that's deployable for physical world applications. And that's the area that Perceptron continues to operate at. Uh, and that's the efficient frontier. So let's dive a little bit further first into the quality of what does it mean to be at the efficient frontier. So let's take video as an example here. And it turns out that even if you look at benchmarks as they are themselves today, they only define essentially half the story. So here's a list of essentially 5 benchmarks that are being used, or sorry, 6 benchmarks that are being used to assess models prime for video intelligence across today's multimodal foundation models. And they range from things from egocentric data to like very perceptive and high frame rate questions to understanding what's going to happen next in a scene to things more related to event prediction and understanding things you expect video models to be able to do. And you'll see a breakdown of scores that essentially align with the graph shared earlier. But the really important thing I want to walk away with here is that when building these models, you can go and maximize for these benchmark scores, and that's essentially what most labs end up doing. We ended up going a little bit deeper in towards we want people that are actually in the video domain and in the image domain to be able to use our models. So when you take a look at these benchmarks, you'll see something like NextQA is at 85% accuracy. So pretty high. Probably from most people, a deployable threshold for what it means to be a video model. Now what we did is we created this hard subset. And what that was is we went through all the examples in each of these or four of these benchmarks and we filtered out examples you can get right with just a single frame. So there would be questions like, is this person going to jump rope? And they're mid jump rope already, and they have a jump rope in their hands. And you don't really need to understand the video to be able to answer, are they jump roping? They're already like mid jump in the jump rope too in the first frame. That's not really a true assessment of where you lie on video intelligence. That really just tells you how image understanding is going, for instance. So if you want to capture a different dimension of quality than what image is doing, you actually have to go and filter down a bit further. And then you really start to see where the deltas lie. Like a model that was getting 70% on egocentric videos, like Gemini 31 Pro, can drop as low as 40% as soon as you filter out things that can be gotten right with just a single frame. Uh, and so the benchmark story starts changing quite a bit, and it becomes like you have to be very strategic in terms of what you optimize for to get true video understanding in your models. And so the big realization I want folks to take away here is that the current benchmarks you see and everything that's being reported, especially in multimodal, are very nascent. We're missing out on a lot of information that we really need to capture to truly build models for the physical world. Okay, so that's on quality, and that covers one of the axes of the efficient frontier. The other is on efficiency and cost. And where cost really starts to become a problem for all physical world and multimodal applications in general is this idea of context bloat. And you've probably heard this a lot through like coding agents and such before. It's this concept of there's a ton of tokens of context you have to reason over. But the realization here is that just the math for context bloat becomes very different when it comes to any multimodal content. Because inherently, a token just means very different things. If I have a token of text that contains way more information than a patch in an image, which contains more information than a patch in a video, like this inherent redundancy and sparsity that's happening across both these domains, or all three of those modalities, that make this a bigger problem to reason over. And it's not just that you have like individual text tokens; you have groups of text tokens, which are fairly compressed. But then you have groups of images. You might own a large database. You might be streaming and always on input. Or you have some form of video, which makes it even worse. So as an example here, consider like the information that information you have to reason over for each of these sentences. There's a text like the forklift entered the aisle at 14:02 and made a three-point turn, stopped beside pallet B12, right? This is a text description of something going on. This is 20 tokens where there's very clear information in every token here. Very important to understand every part of the sentence. Then there's an image of a flower. In this image of a flower, really the main part of detail is just in this region right here. Everything else, there's of course information in that, but there's a lot of redundancy in the background or like the ground and such here. And this, like, I don't know, you might want to write a description of this as a flower. You can go into details of what each of the petals look like. Uh, but this would take up to 1,000 tokens if you naively tokenize those. Uh, Extend this to a video of a car just moving down from a static camera perspective. Of that, the only thing that's changing information, in each of these is the position of the car itself. And to just encode this set of 4 frames, for instance, here, or I think more realistically, this would be closer to 8 frames for this number, but you're getting up to 8,000 token context length. Like context bloat and information across these 3 things varies a ton, where you could even argue the text has the most information here compared to these other two. Uh, but there's order of magnitude differences in the context of tokens themselves. So cost ends up becoming a very big problem because you end up dealing with very large token counts to handle the multimodal cases. And what your 10x difference was earlier becomes very expensive for something like Gemini versus Mark. So a big part of our research into how we build models goes into how do we manage context flow. So we have many techniques, but to talk about two of them. So first is context bloat for token compression. And the idea here is that inherently we should model things differently, where there isn't just one token is the same across all modalities. The ways we represent tokens in text differs from the ways we represent tokens in image and the way we represent them in video. And the way we essentially do this is we have this idea of compression of tokens, where there's a group of tokens that go through some function to be combined into one super token, for lack of a better word. But there's essentially this merged state that makes it so that when you deal with a token, it captures way more information than what a naive tokenization of an image or a video would do. So we start with text and we keep text pretty much the same. Like the existing models, like the BP tokenizers and such that everyone uses, are fairly optimized to address how to optimally compress text. You don't really need to take an action here. So we don't do this for the time being. Then you get into images. And in image, the main redundancy dimension is through spatial. Uh, there's groups of pixels that are more related together, and you want to be able to merge them as well. So Mark 1 deploys the 4x compression rate on images. And what it essentially does is it takes groups of groups of pixels together, groups of patches, and does token merging across them to end up with 4x smaller tokens per image. So 1024 tokens is now becoming something more like 256 tokens. And that's what's going on essentially right here for spatial compression. For video, we take on one more dimension of compression. And so we start with what are the frames of the video, and we do compression on both the spatial axes, which is the same as what happens with images, and one more on the temporal axes. So if you have something like a 2 FPS or 4 FPS video, a group of every 2 frames gets merged together. And what this lets us do is define this essentially cube that represents what something is going on in a video here, of both the time dimension as well as the spatial dimension of what one token essentially becomes. And this leads to an 8x compression rate over what's in an original video. And so both these things essentially let us build in these heuristics of there's redundancy of information in both space and time that we need to account for in multimodality. And this lets us cut down token costs a bunch. And it's something that quant folks do as well. So it's a common way to deal with token compression and token context flow issues. An additional novelty we have here is going further into our model stack. And the idea here is how do we deal with context flow and computation for all kinds of tokens throughout our models when they're inherently different multimodally? So a common way that this is done in the cognitive AI and the text AI space now is a mixture of experts. So if you've heard a mixture of experts, it's essentially a way to come up with a sparse architecture where every token doesn't just activate activates a subset of a larger set of parameters, and these are called experts. So your model might have something like 8 experts, and each token gets to activate 2, and every token gets to activate 2. And this is a way that you can represent more efficiently how a larger model runs, just more efficiently approximate a larger model. The realization here is it's the same problem that we're dealing with token compression, where if you say that every token gets the same budget in the multimodal cases, you end up with something like background patches that are very redundant in images get the same compute that a text token would, for instance, or a higher information region of an image. So what we really need is we need dynamic architectures, things that realize the inherent sparsity of information. And sparsity is that idea of that text is dense, video is sparse, the image is somewhere in the middle. It's an inherent attribute of the data itself, and it can change across different videos, different images, different texts, can be denser or sparse than others. Like think a Where's Waldo image is just much more dense than a picture of a single flower. So computation should change according to the sparsity of the data itself. And so we have this concept of data sparse mixture of experts that essentially let us represent this natively into our model. And so here's a visualization of what's going on, is that let's say that each token is allowed to activate up to 3 experts. So text tokens tend to be ones that have more information, so they might activate all the experts. Then the first image token might have more information, so it also activates all the experts. The second image token might have less information, so it chooses to skip the experts in this one. Third one has a medium amount, activates only 2 of the experts. The idea here is that you can be dynamic in the amount of compute each token gets. And this lets your model be much more efficient in representing multimodal long context input. And this is really a pretty big deal when you end up dealing with this whole context flow issue. So those are the 2 dimensions on both the token input side and the model architecture side of how we deal with context flow that lets us deliver much cheaper prices. Taking this to a more visual level of you can actually visualize what data sparse computation looks like. So on the right-hand side here, you can see that there's a picture of a graph. And what we do is we look at where are we spending compute on this image. And it's really cool. What you end up seeing is that the background, the model isn't really paying attention to, but the axes and the labels themselves, it pays a ton of attention to. And the line of the actual information that's going on here, the model's paying more compute to. So you can see that this idea that whenever there's information present, the model's able to effectively condition to it. Now we can go into this image right here, which is of a fruit stand. And not only can you do this, but because our models are causal or regressive transformers, they can actually rely on the task information to change how they do compute. So if we gave a system prompt for this image right here, that's something generic, like answer the question based on the image, model spreads apart compute fairly equally. You can see there's large regions of compute across the entire image. It doesn't know where to focus, so it decides to focus essentially everywhere. But if you gave it a different prompt and you said something like segment out the fruit before the image, the model conditions on this prompt itself and starts already allocating compute more towards the fruit when looking at the image too. So this idea of our model is inherently more dynamic, is able to reason over, is able to reallocate its compute to reason over images. Okay. And then one of our other innovations here is generally on how we mix capabilities and modalities together. So if you're dealing with any multimodal problems here, and we'll talk more about what they look like in a second, there's essentially a ton of data sets that you're dealing with. Thousands of tasks, petabyte scale data set, trillions of tokens to go about. How do you actually effectively mix these together? So I won't go into this in too much detail, but it turns out that if you try to do any kind of naive mixing of data, it becomes pretty difficult. Um, you end up with too many knobs to tune. It's very difficult to get things done very effectively. What most people do is they pick a couple domains they optimize for and kind of hand wave the rest. We come up with a very principled approach on how we do this, and it's through this meta-learned approach called skill rater. So for the sake of time, I'll skim over this, but the idea essentially is that we can learn ways to mix data by realizing their impact on end skills. So if we want to optimize for capabilities like OCR and VQA, we can give our general training recipe these objectives in mind, and it can back learn how we should be allocating our data in, at the individual example level of how to optimize for these skills. Okay. We talked a lot about what it generally means to be building these frontier models. We talked about that there's improvements in quality. We talked about there's improvements of the cost scale. The question now is, we're at the frontier perception, but what does it really mean to be at the frontier perception? I think Harpreet will show more what this looks like in the Vox layer, but to quickly go through some of the examples, there's essentially 5 things we've realized that we're able to do with these frontier physical AI models that are pretty important to various domains and markets here. So the first one here is native video understanding. So our models consume video at up to 2 FPS, considering up to 256 frames at their full resolution. And this allows us to get very granular annotations and understanding of videos. So here's an example of someone annotating for a robotics task. And so they have a video of a robot doing a task, and then what they want to do is they want to come up with the exact annotation of what's happening at every second, what the robot's up to, and what are the different things it's doing. So you can see that our model here is marking directly on the timeline what's going on, annotating exactly what the robot arms are up to, and they're able to get pretty rich annotations doing things this way. The second thing here is that you really want to care about operating in the grounding domain. Like models really need to be able to understand and point to what they're thinking about. So bounding boxes, individual points, segmentation masks all go about this, where they care about not just answering a question like my laptop is to the left of my coffee cup, but you actually want to allocate where things are and point to exact pixel coordinates of where they are. And that lets you actually build agentic applications where people are able to actually integrate this within their workflows. So here's an example of something that was new enabled through Mark 1, which is very fine detailed hand pose estimation. So each individual joint on a finger is being called out right now, and it's being laid out. And here's a list of the different joints that people are asking for. So this hand pose estimation counting is very fine detail as that earlier models were struggling to do. Something you can do with Mark 1 now. There's also grounding in the temporal domain. So this doesn't just relate to pointing in space, you can point in time. Event detection and identifying exact parts where something happened is a pretty critical component for video agentic use cases as well. So here's an example of when does the firefighter begin to extinguish the fire. We point to the exact second of when they start and they're able to go into the building here. One more domain we've seen become quite useful is not generally in the application, but generally how you interact with models. Often when we communicate to each other, we don't always just talk in text. If I'm trying to describe a concept to Eric, for instance, and I want him to look for a specific cereal box, I don't often just tell him, look for the blue mini wheats box. I'll send him a picture of what that looks like. Uh, and that's a very intuitive way to communicate in the physical world is that why waste time trying to describe something that could be ambiguous? Let me unambiguously give you a multimodal example of what this looks like. It could be an image, it could be a video. So Mark 1 was trained to essentially do this, that if you can take an example of like the cereal box that's in this video right now as an image rather than describing as text, and pass in a video of someone walking through like a grocery store, Mark 1 can point out exactly when it saw the mini wheats box in this case. Now, all that said, we talked a lot about what the importance is of getting quick and fast responses. Reasoning still has its role in the physical world. There are applications where you do want to think cognitively, but about the physical world itself. So this is, I think, one of my favorite examples. There's three clocks here. While the video goes on, you'll see them. Los Angeles, London, and Singapore. And the user asks in this case, what time is it in Portland? There's no Portland clock, but the model needs to be able to reason over it that, okay, Los Angeles is in the same time region as Portland. There's a clock for Los Angeles. Read the time on that clock, and then respond to Portland. And if you enable thinking for our model, it's able to effectively do this as well. And that's the correct time. Okay. And the last thing I'll call out here is that there are classical tasks too that are relevant for everyone, things like OCR. And everything seems to struggle the same way when you compare the digital and physical world, is that you're not looking at structured, printed out text anymore. You're looking at like handwritten documents. The real world just ends up being messy. So our focus on being able to represent things at negative resolution, represent fine details of perception and point and localize them, essentially is an example of how we're able to read like high information OCR forms that are handwritten very effectively. Like here you can see here there's a full form. We're not transcribing everything. We're saying like give me the home phone number. And our model exactly isolates what the home phone number is and calls out the text for it. So you both get the OCR, the localization that's going on. You can see like salary is mentioned here, and then our model is transcribing. Uh, where's salary? Salary right here to $30,000, even though this can be a little bit hard to read. So effective OCR in the real world also just ends up being messy. So that's a summary of Mark 1, and we'll talk more about the integration to Voxel in a second here. But just to give a tee up of how we think about things and where we're generally headed, the way we started Perceptron is we're starting with perception. The Isaac series was all built around images, and it was able to go through and effectively reason over if you have a single image asset, where do you go from there? And that was essentially the key seed to starting with physical world AI. Then we talked about Mark 1 today. Mark 1 essentially said what happens if you have a sequence of images and there's this new dimension of temporal understanding. Now, not just space, but time is moving throughout this model too. How do you effectively understand that? And that unlocks a whole new market of use cases where you want to understand events, actions, and things that are much more present in the real world too. The frontier after this is understanding the consequences behind actions. That if you have two frames and something happened between them, can you predict what that was? And this ends up becoming the primitives of control. So when you start getting into VLAs and robotics too, the idea of there's some action that influences a state between two observations, and being able to model that and predict that is essentially the cornerstone of going into the next frontier of physical AI, which is on control. And that's the next release we'll be doing fairly soon, which I'm sure we'll talk more about when that comes out. But that's a teaser of what we're up to. All right. Thank you all.
Awesome. Thank you very much. So there's some questions coming in into the Q&A widget. If you guys have questions, make sure you drop them in the Q&A widget as well, and we'll get to them. The first question, most important question I saw in here. I think somebody might have deleted it, but oh yeah, it was the question on why is the model named Mark 1? Who is Mark? I see that Eric did drop a link to uh, some Wikipedia article, but yeah, if you just
Yeah,
speak to that quickly, that'd be great.
very briefly, we wanted to own a versioning scheme. So Mark 1, Mark 2 is generally how aircrafts and spaceships name their models. So this was the idea was that this is a very big moment for us, and it's a different series of models than the Isaac models. So It marks the first moment of us releasing a frontier perception model. Now, on top of that, the additional nuance here is if you're familiar with Perceptron, Perceptron we had picked as a name as a homage to the original neural network. The first computer that the Perceptron ran on was the Perceptron Mark One, which I believe Eric linked. So it connects to our name and our background in a few different ways, and that's why we
Awesome.
want Mark One.
Awesome. Thank you. Yeah, and there's a bunch of questions coming in, so we'll go ahead and start addressing these in order. So the first question I have here is how does Mark 1 achieve its 10x cost advantage over some of the larger models like Gemini, for example, while maintaining this kind of frontier level performance on video and embodied reasoning?
Yeah, it's a great question. One is a very particular design behind the data is a very, very important thing. So an example here is that if you're trying to build a coding model, don't use Mark 1. Mark 1's not built to do this. Whereas you can use Gemini 3 Pro as a coding model. So we do have an inherent focus on multimodality and physical world problems that gives us a natural edge. So one is that that focus drives it so that we can achieve similar performance in models that are effectively smaller. So one dimension is that focus, data mixture, curation, studying of the training recipe allows us to be much more data efficient than the largest models that are out there to achieve the same quality. The other big thing here is how we model things like context bloat, the token compression, the data sparsity that we're going after, essentially are like their orders of magnitude improvement in how we can think about training and inferencing efficiently. And we have other tricks like this that we're not talking about, but know that generally this is the theme that I wanted to present, that context bloat plus focus leads to significant cost reductions.
Right. And since you mentioned training data, there's a couple questions here about this. One is how is training data curated to ensure that the model learns appropriate data sparse computation patterns, for example, focusing on informative regions while ignoring redundant backgrounds?
It's all learned, which is the impressive part. If you can do something, I mean, generally speaking, our background comes from training foundation models at FAIR, at AI. And the general learning here has been historically, if you scale up methods effectively on large amounts of data, they inherently learn biases about the data itself. So as an example is imagine trillions of tokens that we train on top of, and you have a bunch of questions and summaries of charts that humans or agents and synthetic data have written or you transcribe with OCR models. There's just different things that we can extract out of these, or PDF documents that mention charts. All of them talk about some information in that image itself. And you realize that to reconstruct, to like extract information of what's in that image, you don't need to pay attention to the background. So what we do is we constrain that, okay, across, I don't know, let's say 1,000 images, you have to spend this much compute. You can allocate that compute however you want. And inherently, some of those images, the only way to do it is allocate more compute to one of those images, less compute to the other. And just over scale, you end up learning these kind of biases. So the really cool thing is that we didn't ever supervise to learn something like this. But it is intuitive that if I asked you to allocate compute, you to learn a policy that's like this. And it turns out with scaling data and scaling models the right way, they also learn the same thing.
And so, just kind of piggyback off that, another question here is about the ratio of video to image data in Mark 1's training mixture. Are you able to speak to that? And then also, how would you
Yeah.
determine that if that balance is optimal for physical world understanding?
Great point. The exact mixture, it's hard to speak towards for a couple of reasons, but know that we focus entirely on multimodal training. So our intention is to be very, very heavy, to the point of I'd say like at least 90% of our data has some multimodal content. Like less than 10% is text only. And of that, video tends to be a decently large chunk of different stages. So to give you an example, early stage versus long context range. Long context stages have a lot more video data than the normal training stages. So it's not clearly it's not an easy to answer question for that reason either. But the general method here is the skill rater method. So there's a full paper on both skill rater and data sparse that go into this in a lot more detail than I'm going to right now. So if you're interested, either read it or feed into Claude, and I'll tell you all about it. But skill rater essentially lets you define the objectives you care about. So what we do is we define the skills that compose the physical world, and we use that to back calculate what should the mixtures be that optimize for those skills. And it gets quite complicated on how exactly to do that and how you filter out data, how you weight data. But it all is essentially built on this meta learning approach that's in skill rater.
And I did drop a link to the archive paper in the chat there. And
Awesome, thank you.
if you're watching this after the fact, there'll be a link in the email that uh, get see the link to Skill Radar. The question I had actually, I guess, is, um, when it comes to figuring out what counts as high quality video data for like physical AI versus like cognitive AI.
Yeah.
And maybe you spoke to it just in your previous answer, but I guess how do you identify and prioritize the data that's going to teach like a really genuine temporal reasoning rather than just like frame by frame, single frame understanding?
Yeah, that was I think one of our biggest challenges in data in general. Is it's not even the single frame reasoning becomes a big part of it, but like a lot of people that build video data sets build it for like math tutorials. And that's not really a physical world problem. They're just trying to teach concepts over a video that can be broken apart exactly frame by frame instead. Or the other big issue is that if you deal with something like CCTV, or okay, I'm going to go on a little bit of a tangent here, but generally, even if you look at videos that people share with each other, a video is cut for another human to consume, which means it's inherently more high information than a video that would be in the real world itself. Like no one generally has like 24 hours of CCTV where like nothing's going on, nothing's moving. Uh, so there's different things that we do here. Is one, we do target domains that we know are more physical world centric. So a big key here, and we talk about this a little bit in our blog post, but I'll share now, is sports ends up being pretty important because sports is inherently a very physical world domain where single frame understanding doesn't help you that much. And we had very specific efforts to dive deep into data for sports and use that as a proxy of temporal and action understanding that wasn't really present in other domains. And if you can start teasing apart properties of what makes that happen, you can start searching for them more aggressively. So things like you can do summaries of videos and look at like the mentions of different actions that are going on. You can identify like talking head segments and try to filter out those as much as possible. You can look for like the codec within videos and realize the frequency of iframes actually tells you how much motion there is in a video, and that can essentially give you some proxy for what's going on. Whereas like if there's a single scene change and such too, you can do that. There's a lot of these heuristics you can do where a lot of it is just diving into the data, to be honest, than I think more principle.
And thank you very much. And a question coming in here from Palomi. Uh, uh, how do you efficiently compress video tokens so as to not miss the right tokens?
Yeah, yeah. Uh, it's it's all learned. I think this is the right way to do this. So the fundamental bottleneck in our approach is that if you don't have enough high quality data that requires knowing the right information, then the model can learn a policy that ends up skipping information that's truly relevant. Uh, so actually, I'll give you a problem set that we have right now that I don't think you can easily solve through our API yet. We're working on actively releasing something for this. Is that we do limit videos into our API to FPS. So there are cases where you need like 10 FPS or 30 FPS. And we have internal models that have larger context length that more easily can scale up to that frame rate that we're just trying to make sure the quality is good enough on before we release publicly. Um, but that's an example of a case where we do actually end up missing some information because even just like the first level of frame selection might just skip some detail that was relevant at 10 or 20 FPS. Uh, so we have solutions for things like this in place, but it really comes down to, I mean, anyone can turn on 60 FPS into a model and feed it into there. Your model will just have the same context flood issues. So you just need to have the right high quality data that requires understanding at that scale and enough of it that your model can't learn these shortcuts, and then learnable approaches like data sparsity can handle the rest.
And thank you very much. And a question coming here from Varun. How do you make the model more specialized for a certain domain? Is it primarily the data? Is it the architecture? A combination of both? Or what's the way you approach that?
It's actually primarily data when it comes to specialization. We try not to specialize architectures themselves because we think that's like you won't build a generalist model if you do that. There are attributes we go after, like high frame rate understanding is an attribute of sports, so you might specialize our architecture to be better at high frame rate. But we don't go like domain by domain, so that tends up being very data mixture driven. Of that, the reason we released Mark 1 is that Mark 1 is meant to be the larger frontier model. So this can fit a lot more into it. It can be a lot more steerable, way easier to prompt and work with than something like our Isaac series, where we have to be a little bit more careful on what kind of data goes in. And we have to make more and more strategic calls simply because it's smaller. That's there. So the main function for this is data, and that too, the main function of this ends up being the post-training and reinforcement learning data.
Awesome. And we'll do the last question here before we jump into how to use the model with our 51 integration. And the question it's actually coming in here regarding the high frame rate data. Uh, do you have to provide the frame times to the model for it to reason over the duration an event takes place.
Yeah, we do this in two ways. So one, you can either pass in the raw MP4 and we extract videos in a specific template that includes the frame times and the relative or well, model knows how to compute relative distances, but it does know the exact time that each frame happened. Or we're setting up a video frames API for the folks that are interested, where you can pass in the raw frames yourself rather than relying on us to do downsampling or rescaling for you, so you have more control over that. For which we do ask that folks annotate what frame times there are. And so that's our mechanism for the model keeping track of time.
Okay, and a lot of really good questions in the Q&A. Won't have time to get to them, but they all are really good technical questions. Can you point us to like a blog or a paper associated with the model release so that folks can read up on that?
Yeah.
Um, if you could drop that in the chat, that'd be great. I'll make sure to include that in the email that we send out. But yeah, very good questions, everybody. So let's see the model in action. I think that's it's time to uh, pedal to metal, rubber meets the road. I don't know what the right expression is. let's let's go ahead and see this thing in action. All right, so um, I am going to drop a link in the chat here. This is a link to the integration of Mark One and 51. Um, I'm assuming most of you guys are familiar with 51, given that you guys are coming from our community. Um, so what you need to do to get started, it's going to be here. I'll add some gifs and whatnot to the README soon. Um, but it's just really quick to get installed. Of course, make sure you've installed the requirements and then download the plugin, and then from there, make sure you set up a uh, Perceptron API key. You can sign up for your API key here, platform.perceptron.inc. And I believe if you enter in the code 51, you get some amount of credits to use via the API. The model's quite efficient, so I think you get something like $1, and $1 will get you quite far with this model. Um, uh, it took me a while to eat through $8 using the model. It is quite cheap to use. But that being said, we're going to see the model in action in a couple different scenarios. So first and foremost, I just want to pull up our quick start data set. If you're at all familiar with 51, you should be familiar with this data set here. This is our quick start data set, just a subset of Cocoa. And now there's two primary ways that we can use the Perceptron model within 51. The first is, we could hit the backtick button, open the operator browser, type in Perceptron, and then a run the whatever task you want to do over the entire data set. We do need to have metadata computed, so let's go ahead and have that done right off the jump. We'll go ahead and compute metadata. So a couple of ways we could run it. We're going to come to this in just a moment. But I think the natural way you might want to use a model, at least like what I do when I try to approach using a model for the first time, is I just want to run it on a few samples and kind of see um, what what the vibe is of the model, right? It's just kind of vibe checking the model, I guess, for lack of a better term. So we can go ahead and see that in action here. We can maybe open up a image here. Uh, and once you have the plugin installed, when you open up a sample, you hit the plus button, and then you should see this, assuming you've installed the plugin, this Ask Perceptron. This opens up just a chat window here, and you can just quickly ask a question like, for example, what is in this image? And of course, we can get back a response fairly quickly from Perceptron that kind of shows us what's in the image or tells us what's in the image. Now, during the presentation, Akshat and Eric, you guys had mentioned that we can do some interesting stuff with this model, get some interesting types of capabilities, for example, grounding or counting and things like that. So if I wanted to, for example, have this Perceptron model just uh, like, can it do a segmentation mask type of thing, or is it strictly bounding boxes on images? Like, what's the capabilities on images that might make sense for this particular image as just like a case in point. Um, what should we prompt here for the model?
So I think one we can start with here is that we can ask to point to the hand that is touching the face, for instance. And this should present a bounding box. You can do segmentation masks. The main thing is that they're more expensive and slower.
Hmm.
So we often find for speed reasons, we tend to prefer bounding box over also individual point.
Okay, so we'll go ahead and say that right here to the model. Point to the hand that is touching the face. The model will run. The hand touching the face is the left hand. If we wanted to get back like the actual kind of bounding box itself, should I say like draw a bounding box around that, or is there a uh, specific kind of way to get the actual bounding box, or like draw a bounding?
Does this native, yeah, you can probably get it through textual cues, but in the vision config, if you just specify point as the return type, it should also, yeah,
Okay,
point box.
right, yeah. So a little bit of um, playing around with the model, figure out how to get it prompt, and then obviously you want to see it right here in action. So with this integration in the chat panel, one thing you could do is, assuming we get, uh, assuming we prompt it for some particular type of output, we can parse it right into 51. So I'll say this: convert to 51. Once we do that, we want to hit refresh on the browser. We hit refresh on the browser, and we can see right there that we get a bounding box around the hand, right? What we could do now is, you notice that it tells us here point box and gives us the uh, coordinates that we then parse. But we might want to go ahead and change the label, or maybe update the label, or even make the bounding box tighter. So what we could do now in 51 is go to the annotate tab on the sample modal here. We'll add the schema, go up to the field that we just added, Perceptron detections, hit setup. Everything looks right here. It's the detections, got all this stuff, right? And then what we're going to do is we're going to edit the detection. So the way we can edit the detection is perhaps we just want to change the name. Maybe the name here could be hand, just hand, right? And we might want to draw the bounding box a little bit tighter if we wanted to. So we can go ahead and do that as well. And we save that. So this gives us a real quick way to bootstrap kind of data collection, right? If we're able to quickly ask the model to find something, and then gives us an output, and then we use 51, the new annotation features in 51 to adjust the bounding box. We're able to do that. So that's just one way to use the model here. Just on a single sample, on a single image itself. Next is, we can run it on the entire data set. I'm not going to do that now, but there's some things that we want to point out here that are useful for using the model. So Akshat, can you talk to us about, these configs, parameters for the model, one of them being enable thinking and enable focus. Like, what does enable thinking do, and kind of when do we want to use that versus when do we not want to use that?
Yeah, yeah. So generally speaking, one thing we did with this model is we added this concept, this vision config, which Harpreet is putting into Vox 51 for the reason of people that want to interact with these models need some kind of steerability and control. And we want to make sure we abide by that control and steerability with one model that can kind of do everything. So there's essentially three knobs that I think make a difference here. One is the output format itself, which we're talking about. You can control box, point, polygon this way. Because you can imagine the same question, whether you want to do left hand or right hand, you could point to different kind of output structures, which Harvey just sold. The second one is enable thinking. So enable thinking is our way to turn on test time compute for our model. So you start using up more output tokens when you want to do this, but response qualities generally tend to go up when doing this for responses that require reasoning. You might be able to trip up model in some edge cases here, so there's some general guidance we have in mind. But it's one model that does both thinking and non-thinking rather than two separate thinking and non-thinking models. So one way we do this, or like one recommendation we have is that if you have anything that requires some kind of, like it would take you a second to reason about it, like the Portland clock example that we talked about earlier, uh, reasoning over spatial relationships, things that are more than a one-hot query, we recommend turning on reasoning for. In fact, generally, any kind of visual question answering query or any question answering query, or even summarization tends to improve with reasoning. It still works without reasoning, but quality tends to improve. So that becomes more of a user thought on cost and latency. Do you want to spend more for the higher quality and the slower latency? The examples where you shouldn't turn on reasoning is things like if you want to point to specific objects very, very quickly, like the left-hand example went through. Super easy, it's natural to perceive. You shouldn't turn on reasoning. It's going to waste tokens to do this. You don't need to worry about that. So generally, I think the thing comes down to if it's something a single hop, quick to reason over, don't use thinking. If you care about cost, also don't use thinking. But if you care about quality and are okay waiting a little bit longer and general question answering and analytical questions, then turn on thinking.
And then focus. When do we want to use focus? Is this primarily for like visual grounding, or is that?
Yeah, focus is a very, very interesting thing that I actually didn't talk too much about in this talk. Maybe I should have. The idea of focus is our model has a very specific form of test time compute where it allows the model to essentially focus on a region. And what that does is it acts like a model level zoom, is the way you can think about it. So the backstory for this is that when we were working on different grounding tasks, we saw our annotators, when they would annotate something, would actually zoom into the image to find small objects. And so we wanted our model to have this similar capability so that, like, why should the model have to do a strictly harder test than the human? So for this reason, focus came in, and focus is meant to be that area where you want to really, really answer that zooming aspect. So it's not something I would recommend turning on generally. It's meant to improve in a very specific set of cases. So one is that if you're trying to find something that you felt like you would have naturally zoomed in for, like very small objects and such, then focus may help. If you're trying to talk about a reasoning question that does multiple things, so there's this example of that we have on our website actually, if you go to the Perceptron demo of PPE equipment detection. So like the model has to zoom in to like the heads, the hands, the feet to make sure everything is being properly addressed from PPE. And that's when we used focus for that either, because there's like multiple things you have to zoom into and check some detail about. So it's a cool feature of a very specific test time compute that helps essentially in small objects or in many objects you want to go reason about one by one.
Awesome. So I'll go ahead and let that run here real quick. So it might take a few seconds here in the background, but I just took a sample of the data set, and here what we're doing is you can see it's going pretty quickly over this 10 samples, and I prompted the model to find human heads. So we're going to see this output here, and we can see that the image on the lower right-hand corner here is got a bunch of small human heads, and so we could see that the model does fairly decent job here. Human heads is classifying all of that as a human head, but on this scene it does quite well, and you can see that there's great bounding boxes here for human heads. So that's just a quick way for you to use the model here on images. On images, you could do a semantic search, just a natural language query if you're trying to find images that contain something in particular. You could also bootstrap labels. That means if you have a completely unlabeled data set and then you want to try to bootstrap labels really quickly, you could run this on your across your entire data set and make that work. But now I want to change the type of data set that we're working with here and look at this data set here of just short video clips. Now, this is a data set that is part of ICRA. I just came across it earlier this week. I thought it was an interesting data set. And so I figured we might as well play around with this data set a little bit. We're just going to take a random sample here. I'm going to add a take stage, and just in the interest of time, I'm just going to take 5 videos. And real quickly, the first thing we want to do, of course, is we can open this Ask Perceptron chat window and ask it really quickly to just describe what's in the video. So you can enable thinking or disable thinking. And we can just say describe the video, and you'll see we'll get a response back for that. And then we'll see how to use it on what we call temporal detections in a second as well. So you can see here we get a real quick response from the model. Is there a particular length of videos that the model tends to work best with, or like is it short clips or longer clips?
The part that I think matters the most is the density you want to go after. So the if you want full fidelity understanding of a video, the most optimal thing here is probably 2 minutes at 2 FPS. The entire thing will be consumed with no truncation. And our model linearly scales up from there. So we do actually quite well on 10, 20-minute videos too. We just sample at a slightly lower FPS. Uh, the cases I wouldn't recommend out of the current API until we start a long context API, which will come soon as well, is things close to an hour. For 30 minutes to an hour is probably where we're downsampling enough that we'll be skipping more information than you'd want, primarily just from the way we're serving our API. So would recommend keeping things at like the highest resolution cases in the under a few minutes mark. Medium resolution, you're okay downsampling the 10-minute mark should work, and then you can stretch to get the 20-minute to 30-minute mark to work.
And you can see here, while Akshat was giving us the explanation there, I prompted the model to just clip out the segment where the rickshaw crosses the intersection. So we can see here that there is a rickshaw that crosses the intersection. And we get back this response from the model. And we're just going to convert this into 51 label type. We'll hit refresh there. And then we'll have a temporal detection here, a perceptron event, as we'll call it, that will parse when this event took place. I save it as perceptron event. Yeah, so this is likely just an error kind of reloading the app there. Yeah, and we'll get the event shown up here. Well, it gives us this right here at 0.3 seconds and lasts for 2.7 seconds. So that's just a small little issue that I'll need to fix on my end. You can see that this integration is, some parts of it are hot off the press here, as you can tell by the commit history. But we could also do some other stuff with this integration, of course. Run it on the current view. We could do event searches, semantic searches, and bootstrap labels. So Akshat, when would be let's just say we have like a data set of small video clips. You know, when should we use something like a event search versus like a semantic search? Like what use cases would these kind of operation modes make sense with the model?
I think user dependent on what the outcome you want is. Would recommend these event search of getting like the exact timestamp things if you're trying to build something that requires just going directly into not just did something happen, but when did it happen. Like use cases we see this become pretty prevalent and is like highlight detection. You want to go and do like a second round of analysis over something. You care about a second pass of information about like not just did the event happen, but like I want to know exactly what that is. Maybe you want to answer more questions about it, dive further into it, recrop that, interact with it. If there's something you want to do about that event, would recommend that. Um, if you don't want to do that and you just want to essentially like, I don't know, find all of the videos that had a crash in them, then don't take the overhead of doing the event detection. Just do the yes, no. It'll be a little bit faster, which will especially matter when you scale this up.
And one more thing that I think folks may increasingly be doing on Voxel is annotating more robotics and egocentric type data.
Mhm.
And so if you're looking to pull out the exact sequence of events that took place in order to train over that or validate the quality of it, that's another use case that we're seeing big labs use as well as sort of like open source devs.
Yeah, definitely. We can, kind of do something like that on this video clip. For example, uh, does this is a synthetic data set, but does the model care about synthetic data versus real data? Do you notice any performance difference between the two?
We tend not to. Both tend to work.
So here we're looking at a data set. This is just a small subset of the Libero data set. As we say, when does the gripper pick up the cup on the left? So we'll go ahead and run the inference and we'll get back. It says here at 15 seconds. So we let the model run. We can scrub down here to 15 seconds and you can see that That's about when it picks up the cup on the left. Exactly. So quite nice to see that in action. Um, so while Akshay was talking, I'm just like trying to show you guys how to use this model in a number of different scenarios. But something that was interesting to me was a data set here that is also at ICRA called NaviTrace. And let's just subset here. So what I want to do is show how this kind of, we talked about the model working in the physical world. I was playing around with this just a little bit, and just we'll see in action. I'll just show you in a second here. So essentially, what this data set does, it just kind of draws out like paths that a human would take, a legged robot would take, a bicycle would take, so on and so forth, right? And here it's given a task. So enter the parking lot and stop there. So we can ask the model to enter the parking lot and stop there and return points along the way. I'm not sure if that's the right way to exactly prompt it. When I was playing around with it a little bit, that did work. But if you have any tips on how to prompt it the right way, actually, that would be amazing. But here, so you can see we're enter the parking lot and stop there, return the points along the way. So here's the steps that a human would take. And then we'll parse this as a 51 label once it's complete. And I'm pretty sure it'll give us a nice series of steps. I should probably have had it give me far less, prompted to give me less. But you see here it's outlining the steps that you would take to enter in to the parking lot, which is way back there.
That's actually a pretty cool thing. We hadn't tested out many of these use cases of this is an image, right, where you're trying to lay out the path that someone's taking.
Yeah, yeah.
Yeah.
Uh, and we'll just say
Or you
return
might want to
5
add
points.
like use point boxes or something like that at the end of it.
Okay,
And it just will encourage the formatting to be a little bit more aligned. This is something that's being updated right now.
okay.
Um,
Yeah,
yeah.
so what's happening in like to use this in 51, like there's a few things to implement here, but the integration looks specifically for the tokens that the model outputs, in this case for the point box that he's mentioning. So we see here we got point boxes.
You might also want to clear conversation history. I think that's the other thing
Yes,
from
yeah.
it off a little bit.
Well,
Uh,
yeah,
But
in any
this
event,
is cool because one of our next release that's actually coming up right now is trained to do exactly things like this because that one's designed to be very robotic centric. So it improves on both robotic control and robotic perception a lot more. And that one's also going to be an open source model. So for folks that are interested, you'll have full access to that one. And we do these kind of tasks about like predict where the gripper is going to move to, or what's the trajectory of the gripper, or like where are the different points going to move to over time. This like future prediction idea. We're very actively targeting something like this. So impressed that's working at least a little bit in some of these cases here, and then expect to be faster and open source like within a month.
awesome. Yeah, yeah. I was playing around with it a little bit. I had some good results, and yeah, it was pretty cool to see that. Um, And yeah, so just encourage you guys to check this out. The integration is here. Of course, 51's open source. This integration is open source. You get dollars worth of free credits to play around with if you use the code 51, all caps, when you sign up. And playing around with the model and kind of see it in action. I've tried to make it as easy as possible for you guys to get started here with 51, using the model, whether you're using it on images or video data sets. You can get up and running quite quickly with this. So that being said, I just want to say thank you guys for being here. I appreciate you guys joining in. If there's any remaining questions, please do let us know. Give the model a try. Check it out. And huge congrats to the Perceptron team for the great release.
Thank you for having us, Harpreet.
Cheers. Thank you, everybody.
Thank you all.
Thank you. Thanks, Harpreet.
Yep.